Thanks very much for having me, guys. I'm really pleased to be here. As I said, I'm Chiara Holgate. I didn't say I'm a postdoc actually at this Australian National University, and I'm part of an Australian Centre of Excellence for Climate Extremes, which partners with 4 other universities that you see there. So I'm hoping what you might get out of this talk is a bit about what we've learned about the physical processes behind some of Australia's climate extremes from using moisture tracking. And to show that, I'll summarise 3 or 4 studies, but very much invite your feedback, your comments, how it relates to your work or the work of other people you know. Very much open to collaboration, so please do get in touch. So, of course, by the looks of things, I'm going to talk to you about Australia. So I'm wondering what, images come up in your mind when you think of Australia, whether it's nice beaches or forests or unique wildlife. I hope, because all those things are true. But it's also a land of climate extremes. There's always something going on, whether it be floods or droughts, heat waves, extreme wind, which is shown in the top middle there. That's a transmission tower, or extreme hail. This is our Parliament House in Canberra. I live in Canberra, and this is also Canberra, bushfires. So yes, as I said, there's always something going on. And as you know, all these extremes cause loss of life and property, disrupt food chains, compromise water security, and so on. You may also be aware that, in Australia, our rainfall variability is very high, and we swing between drought to flood and back again. And so the work I do is looking at the water-related climate extremes, such as droughts and floods, which will be today's focus, mainly droughts. So we've still got some way to go in understanding how droughts and floods develop in Australia, and that's partly because each event is so unique, and so it's hard to derive commonalities, but also there's a wide range of physical processes that influence our rainfall, which is what I'm showing in this diagram here. And this diversity and complexity of processes makes prediction of these climate extremes and community preparation for their impact quite challenging. So today I'm going to focus just on Southeast Australia, as shown by this very scientific yellow smiley face here in the diagram. Not just because this is where I am in Canberra, but this part of Australia, over half of our agricultural output comes from this region, not just for Australia, but exported to the world. So we're talking about food security. Southeast Australia is also where much of our population lives. So we're also talking about water security and emergency management. So I'll start just by mentioning, some things we do know. Let's look at the sources of moisture for Southeast Australian rainfall. So during my PhD, I used the Lagrangian back trajectory model based on the work of Paul Dermire and co. And this particular model was driven by a WRF-based regional climate model, which was itself forced by Era interim at the boundaries and spectrally nudged above 500 hectopascals. And this particular variety of moisture tracking model, we start with a time series of rainfall like that one on the left, and we break it up into small pieces that we can track. We then launch those air parcels at a random humidity weighted height in the atmosphere, and then we track them based on 3D winds. And the parcels can gain moisture from the underlying surface ET and lose it through rainfall. And so we tracked rainfall every day for about 35 years in Southeast Australia. And so on average, this is where we see the moisture coming from. So that's what the shading shows, the mean moisture contribution to rainfall in the green polygon. So that's actually the boundary of the Murray Basin, a very significant river basin here in Australia. And you can see that much of the moisture contributing to rainfall is from the ocean. So from the Coral and Tasman Seas, which is the Western Pacific, as well as the Southern Ocean, but also the East Australian landmass, and some of it within the region itself, which we see the average rainfall recycling ratio I've got up here, which is probably a lower estimate, but this is an average over many years. So of course, this is a mean over many years. So there's a lot of variation between seasons, between years, and of course between rainfall events. But something we do see by looking at the climatology is that these sources have been changing over the last 3 or 4 decades. So the Tasman Sea and the Southern Ocean have been contributing approximately 5% per decade more moisture to the region during summer, which corresponds to the observed positive trend in rainfall that we're seeing in this region. But this is countered by a decrease in contribution from these oceans in winter, with an accompanied reduction in the rainfall recycling ratio in this region in winter over the last 3 or 4 decades. And this is significant because winter is really the important season for filling our reservoirs in this part of Australia. So, of course, the question that arises, what causes swings in these moisture supplies, considering all these different rainfall influences. But we'll start off today just by looking at how some of the large-scale modes of climate variability influence moisture and rainfall, and try and dig into these teleconnections a bit to get a deeper understanding of the physical mechanisms influencing the rainfall extremes. Today, I'm going to highlight ENSO, the Indian Ocean Dipole, and the Southern Annular Mode. And we can ask the question, how does the interaction of ENSO with the IOD and SAM modify rainfall and its moisture sources? Now, although these climate modes have been very well studied, we're here using moisture transport to look at the processes from a different perspective. And we can dig into this teleconnection and say, are these modes affecting our rainfall because they're actually affecting the evaporation in the key source regions, for example? Are they causing a reduction in evaporation? Or, do those regions evaporate the same amount? The same amount of moisture is generated, but it gets transported elsewhere and away from our region. Or does our region receive the same amount of atmospheric moisture, but local conditions are not conducive to precipitating that available moisture? So in this particular study that is down here, we looked at the combination of La Nina and El Nino in neutral ENSO with the positive, negative, and neutral phases of the other 2 modes. So lots of different combinations, which I won't show you all today. I'm just going to highlight El Nino and La Nina. So first, we'll look at El Nino. Now, in each of these slides, I'm showing you 4 panels. They're all anomalies from the long-term mean, blue being above average, red being below average. And the first panel is the anomalous moisture sources during El Nino months. So standalone El Nino months, so when the other phases are in their neutral phases. Now, there's a lot of rainfall variability during El Nino, but overall, we get a negative rainfall anomaly, so it's often dry during El Nino. Now we're looking at the Darling Basin, which is in Eastern Australia, closely connected to the Murray Basin, which I showed you before. But as you can see from the shading, during these El Nino months, we have less moisture being contributed to our region, and the low-level wind vectors shown here indicate the moisture that we see is important coming from these marine regions is being transported away. Where during these El Nino months, it's typically drier, so we're seeing less evaporation than normal. That's what this negative 15% indicates, which makes sense because, we're getting less rain. But interestingly, during El Nino months, the total precipitable water anomaly was essentially negligible, which was a bit surprising, especially to some in Australia who equate El Nino with drought. But we didn't see a consistent change in El Nino months. We also looked at 500 hectopascal vertical wind speed anomaly as a way of indicating that large-scale uplift. And we see during El Nino months, we get a very clear reduction in that vertical uplift, or an increase in subsidence, meaning that whatever moisture is there is going to be harder for it to precipitate. So overall, we saw that there was less uplift during El Nino, but little change to moisture. And this contrasts with La Nina. As you can see, there's an increase in the moisture being contributed to this region of interest during standalone La Nina months, typically giving us a positive rainfall anomaly. And we see quite a clear pattern of increased easterly transport of moisture into our region. And when there's more rain, there's more evaporation. But importantly, there was quite a clear signal of an increase or a positive anomaly in total precipitable water during these La Nina months. And that was accompanied by an increase in that mid-tropospheric uplift. So not only is there more moisture available during La Nina, but it is more likely to be precipitated out. So overall, we're saying that La Nina enhances large-scale moisture transport and uplift. Interestingly, before I go on, the combination of La Nina and the positive phase of the southern annular mode, so when those mean westerlies shift poleward, gave the largest impact to Eastern Australian rainfall. Really a very wet situation. And that particular combination of modes was at play during the floods of Eastern Australia in 2022. But here we're talking about drought. So in that previous study, we learned about how these large-scale modes affect our rainfall sort of on average, but now we want to dig in and look at droughts specifically. So here I'm looking at 3 individual droughts, 1982, 94, and the early 2000s, which was the Millennium Drought. And you can see from all 3 droughts, there's obviously been a reduction in the moisture supplied to rainfall in that region. But the question, of course, is why? Why did we have a reduction in moisture contribution during these droughts? So I won't show you heaps of plots. I just wanted to say that digging in, we found that it wasn't because those key marine source regions evaporated less. It really didn't change much. But our region received less moisture because that marine moisture was transported elsewhere. Plus, also the large-scale uplift was suppressed during drought, meaning the atmosphere was less favorable to precipitate the moisture. Indicative. You might think this is indicative of synoptic conditions that bring dry weather, but actually, and I'll show later on, it's more about a lack of very heavy rainfall events that separate this region from drought and non-drought. So if we look at the end of these droughts, we can see that the situation reversed. So in all 3 cases, we had anomalously strong easterlies advecting moist marine air from the Tasman and Coral Seas into the region, which could contribute to rainfall. We found that about 5 to 6% of that extra moisture was recycled by the land to form more rainfall, amplifying the wet conditions. And it's just clear how crucial the moisture from the nearby oceans is. So from this particular study, we saw that we really need to better understand this easterly flow of moisture and investigate its variability, not just its variability in regard to those large-scale climate modes, but also from synoptic scale weather systems, especially during drought and drought breaks. And that leads me to the last study that I'll highlight today. In this study, we wanted to find out, which processes are conducive for getting that moisture from the ocean over to the land. And so in this particular study, we looked to uncover those dynamic synoptic scale processes responsible for that change in the moisture supply. And we already know, of course, a few things that can help us form a hypothesis. We know that the moisture needs to come from the Tasman Sea, at least primarily. We know we need a lifting mechanism for that moisture to rain out. And we know that when we have a deep low pressure system, it's conducive to strong rainfall. So when we have when we have a low pressure that is present not only at the surface levels, but up throughout the troposphere as well. And one way of transporting that moisture westward from the ocean is with a high pressure system, which rotates anticyclonically here. And so we can hypothesize that if the atmosphere is organized in such a way that we've got a high pressure system over the Tasman and a deep low pressure system over Southeast Australia, then moisture convergence could be high and maybe we'll have a good chance of rainfall. Now, we saw an example of this particular setup in March 2021, where we had a high pressure system over the Tasman Sea for a few days, combined with a low pressure system that moved over Southeast Australia. Now, this particular event set the record for the wettest week since 1900, and there was very widespread devastating flooding all across Eastern Australia. interestingly, the record that was broken then was subsequently broken a year later, because in Australia we like to break climate records all too often, it seems. But in this study, we used an objective cyclone tracking algorithm to identify the cyclones and anticyclone tracks as they pass through our region, and that was based on Year 5 reanalysis. So we could identify all the days with this particular setup of interest, and not just when we had a high and a deep low, but maybe days where we had a deep low but no high, or we had a high but the low pressure system was only present at the surface or only present, higher up. So all these sort of combinations. And we could combine this information, this synoptic information, with the Lagrangian moisture tracking that I showed you before. And this allowed us to ask, does this Tasman high and deep low event, does it strengthen moisture convergence as we expect? Does it produce rainfall that's heavy or extreme? And does it play a role in breaking droughts? And when we had a look, we actually found, well, yeah, it does actually strengthen regional moisture convergence. So this diagram you're seeing here is the mean daily moisture convergence into the Murray Basin over all days that are shown in grey. And we can see when we have a Tasman high and deep low, that moisture convergence strengthens typically. And indeed, when we look at the moisture sources, we can see that there's a stronger supply of moisture from the Tasman Coral Sea when we have days that have a Tasman high and deep low, compared to days where we might have a deep low, but we don't have a Tasman high. So the days where we have a deep low and no high, it's still raining. We still have this deep low pressure system, but we just don't have that high over the Tasman, really strengthening that flow of marine moisture into our region. Now, we also found that extreme rainfall was more likely when we have this particular synoptic setup. So this plot shows cumulative distribution of daily rainfall across the Murray Basin. And if we, for example, if we take extreme rainfall to mean rainfall above the daily 98th percentile, then of course we're going to expect extreme days about 2% of the time by default. But this is for all days in the region. And we can then look at, we can separate it by the synoptic type of the day. So when we have the Tasman high, deep low, or when we have the high but no low, and all those different combinations, which is now what you see. And what we found is that it turns out the Tasman high, deep low event produces extreme rainfall a lot more often than when we consider all rain days. So in other words, when we have this particular synoptic setup, the chance of extreme rainfall more than triples. But even more interesting to me, at least, was that this particular synoptic setup is really crucial for breaking droughts in this region. So this bar plot just separates the days when we have a high and no high, and then the different situations with the cyclone over Southeast Australia, whether it's deep, it extends into the troposphere, or whether it exists only in the upper part or the surface part or not at all. And then the colours are in brown when we have drought months. So this has been defined as SPI 3 below -1. The opposite when we have SPI 3 above +1 is in blue. And then green are a subset of those wet months. So just the wet months that follow the droughts. And what we can see here is the contribution to total seasonal rainfall by each of these synoptic setups. And very clearly, the days when we have a Tasman high and deep low are very important to rainfall during drought breaks. And the grey portion of the bars are the amount of the rainfall, the contribution of the rainfall that is extreme, so above the 98th percentile. So we can see there's a very big jump in extreme rainfall between drought here in brown to the drought break. And we found that the frequency of these particular synoptic events didn't change a great deal between drought and drought break, but it's really the intensity of the events that really made the difference. So I'll sum up from there. And I guess my point was that moisture tracking helps us to understand the physical processes of these climate extremes, particularly droughts and drought breaks. And then we can use that information to probe further and hopefully improve our weather and climate models and their prediction and projections. Now, so far, we've used the moisture tracking work. We've identified the source regions, that those source regions are changing in some parts of Australia. We've used them to understand the mechanisms of individual droughts, and more recently, the mechanisms of drought breaks, which has been interesting. Looking ahead, things I'm interested in exploring are the processes causing the swing from drought to flood. So from the most recent study, seeing how drought breaks are really tied to extreme rainfall events. In fact, it's really only a handful of really heavy rainfall days that separates us between drought and drought breaks. So, and those drought breaks can lead to flood. So I'm interested in those particular physical processes. I'm also interested in understanding how future moisture source changes impact or can tell us about future water security. How well do these climate models represent the identified mechanisms, for example, the Tasman high deep low days? So we're talking now about model process evaluation. And lastly, how do the moisture sources differ between models and data? So that would be the intercomparison project. And I'll stop there and say thanks so much for listening.
Thanks a lot, Chiara, for this very interesting talk. So I'm pretty sure there will be some questions for Chiara. If not, I'll just kick it off, and then probably there will be some more questions. I noticed, Chiara, in this last work that you showed about this drought-breaking event, so you kind of showed that, well, you need the combination of Tasman high and deep low. But at the bottom on this slide, there is of that slide number 20.
Yeah.
You refer to a paper which starts with anthropogenic warming reduces the likelihood of drought-breaking extreme rainfall events. So where's the anthropogenic warming come in here?
Very good eye for detail, Ruud. Excellent. Yeah, I cut it out actually just to save on time. But yeah, so we were looking at historical drought and drought breaks, but then I went and looked at a number of, an ensemble really of regional climate models to look at how things are currently being projected for the future. And this particular event of the Tasman high and deep low is projected to decrease in frequency under a mid and high range emission scenario by the end of the 21st century, which is certainly concerning for us because it suggests, droughts will be harder to break, at least in the way they have in the past, in the future, meaning that we might be at heightened risk of staying in prolonged drought. So that was one of the conclusions of that particular paper with regards to future changes.
And but you did that based on, there was not really any moisture tracking involved in the climate models. You kind of just studied how often that occurs in the climate models.
Yeah, so the sort of future component of the study used regional climate model projection output, and then we tracked cyclones and anticyclones in those regional climate models to say something about how, often these events were happening. We also looked at other characteristics like how intense they were and so forth, but it was really the frequency drop that stood out.
Okay, cool. Very nice work. Thanks again. I see Chris has a question.
Yes, thank you. So we have very interesting studies. So I also had a question on this last study. So I was wondering how the role of orography was. It is also playing a role because I can imagine that. So that, like in Europe, it plays a huge role in regions where you get these extreme precipitation events. But I'm not sure if I'm not that familiar with Australia, if that happens in this particular.
So it plays some role. So sort of along a spine, along the eastern part of there's where there's a mountain range, and that mountain range plays an important part for rainfall on the eastern side of the range. So systems coming from the ocean and being uplifted and will rain out on the eastern side of the range. But on the western side, where I was looking, it plays Some are raw, but to a lesser extent, because often these systems are coming from the west and raining out before hitting the mountain range. So I'd say it plays a small role, I guess, in answer to your question.
Okay. So it's mainly synoptic than lifting.
I think so.
Okay.
I think so, yeah. Yep.
And a very small other question, if that's still allowed, about this.
Go ahead, Chris.
Yeah, so what for me was the question, so how do you distinguish between a deep low and a low? Just different levels in the atmosphere that you...
Yeah, different levels. So we looked at cyclones at 500 hectopascals, and as well as at mean sea level. We had them at different levels as well, which a separate study looks at in more detail. But for this one, I was just looking at, the previous study found that if you had them at sort of levels between mean sea level and 500, then you typically only need to look at mean sea level and 500 because that's where they would be. So that's what I took here as a way of categorizing the days.
Okay.
Thanks. Fendi, you also have a question?
Yes, I have things actually, but first of all, thank you, Chiara, for your excellent talk. Really well prepared. My first question would be your early slide about the effect of the El Nino on the moisture source contribution. Like you showed two cases, right? The case of El Nino and La Nina. And I was quite interested because, for example, the second panel, there's no significant change of the ocean evaporation, like offshore of Eastern Australia. So I was wondering, did you also look at horizontal moisture transport to actually to verify the change in moisture contribution anomaly?
So did I look at evaporation over the ocean specifically?
I mean, a horizontal moisture transport. Because I think you look at evaporation, total precipitable water, and vertical, right? The pressure velocity.
Yeah. Well, the first panel, I guess, is not only looks at the horizontal moisture transport, but the transport in 3 dimensions. So that would incorporate the horizontal component of that moisture transport. So that would be taken into account here because the moisture tracking was 3-dimensional. Is that what you're asking?
Yeah, but I was wondering if you can also like look at how the atmospheric circulation is changing. I mean, maybe you can decompose this component.
Yeah. Other people have actually, and they've looked at just that horizontal easterly flow, and also came to the same conclusion actually that it was very important to the level of rain that we get in this region. But yeah, I also thought it was interesting that there was little evaporation anomaly over the marine source regions during El Nino, and it's something I'd like to dig into more. I think, remember, this is a composite over many El Ninos, and something that we're grappling with here in Australia, and probably other people in other countries as well, is this diversity between different El Nino events. And so this composite, this mean picture here, I think hides a lot of detail in that event-to-event diversity. And so we might see an evaporation anomaly between different El Nino events. And that's certainly something I'm interested in looking at some point.
Okay, interesting. My second point is the second part.
Fanny, I'm sorry to interrupt you, but maybe in view of time, we should. We should move on, and
just
email me.
Yeah. Because I believe, Chiara, you have to go now, right? You have to.
I'm so sorry that I have to go. Yeah, I have. I need to go to Parliament House today, actually, and speak with a senator about water extremes. Which is not something I do every day, but I kind of have to go.
Not something you do every day, so good luck.
No, it's not.